Well, let's see. Now you know how to make an iterative procedure, or a procedure that yields an iterative process, turn into a machine. I suppose the next thing we want to do is worry about things that yield recursive processes. So let's play with the simple factorial procedure. We define factorial of n to be if n is 1, the result is 1. Using 1 right now to decrease the amount of work I have to do to simulate it. Else it's times n factorial n minus 1. And what's different about this with this program, as you know, is that after I've computed factorial of n minus 1 here, I have to do something to the result. I have to multiply it by n. So the only way I can sort of visualize what this machine is doing, because of the fact, think of it this way, that I have a machine out here which somehow needs a factorial machine in order to compute its answer. But this machine, the outer machine, has to exist both before and after the factorial machine which is inside. Whereas in the iterative case, the outer machine doesn't need to exist after the inner machine is running, because you never need to go back to the outer machine to do anything. So here we have a problem where we have a machine which has the same machine inside of it, an infinitely large machine. And it's got other things inside of it like a multiplier, which takes some inputs, and here's a -1 box and things like that. You know, you can imagine it's sort of, that's what it looks like. But the important thing is that here I have something that happens before and after in the outer machine, the execution of the inner machine. So this machine has to have a life. Okay, it has to know, so it has to exist on both sides, time sides of this machine. So somehow I have to have a place to store the things that this thing needs to run. Infinite objects don't exist in the real world. And what we have to do is arrange an illusion that we have an infinite object. We have an infinite amount of hardware somewhere. Now, of course, illusion's all that really matters. If we can arrange that every time you look at some infinite object, the part of it that you look at is there, then it's as infinite as you need it to be. And of course, one of the things we might want to do, just look at this thing over here, is the organization that we've had so far involves having a part of the machine, which is the controller, which sits right over here, which is perfectly finite and very simple. We have some data paths which consist of registers and operators. And what I propose to do here is decompose the machine into two parts, such that there's a part which is fundamentally finite and some part where a certain amount of infinite stuff can be kept. On the other hand, this is very simple and really isn't infinite, but it's just very large. But it's so simple that it can be cheaply reproduced in such large amounts, we call it memory, okay, that we can make a structure called a stack out of it, which will allow us to, in fact, simulate the existence of an infinite machine which is made out of a recursive nest of many machines. And the way it's going to work is that we're going to store in this place called the stack the information required after the inner machine runs to resume the operation of the outer machine. So it will remember the important things about the life of the outer machine that will be needed for its computation. Since, of course, these machines are nested in a recursive manner, then in fact the stack will only be accessed in a manner which is the last thing that goes in is the first thing that comes out. So we'll only need to access some little part of this stack memory. Okay, well, let's do it. I'm going to build you a data path now, and I'm going to write the controller. Okay, and then we're going to execute this to see how you do it. So the factorial machine isn't so bad. it's going to have a register called a value, where the answer is going to be stored, and a register called n, which is where the number I'm taking factorial will be stored, factorial of, and it will be necessary in some instances to connect val to n. In fact, one nice case of this is if I just said over here n, because that would be right for n equal 1 n, and I could just move the answer over there if that's important. I'm not worried about that right now. And then there are things I have to be able to do. Like I have to be able to, as we see here, multiply n by something where something in val, because val is the result of computing factorial. And I have to put the result back into val. So here we're seeing that the result of computing a factorial is n times the result of computing a factorial. Val will be the representation of the answer of the inner factorial. And so I'm going to have a multiplier here, which is going to sample the value of n and the value of val, okay, and put the result back into val, like that. I'm also going to have to be able to see if n is 1. So I need a light bulb. And I suppose the other thing I'm going to need to have is a way of decrementing n. So I'm going to have a decrementer, which takes n and is going to put back the result into n. That's pretty much what I need in my machine. Now, there's a little bit else I need. It's a little bit more complicated. Because I'm also going to need a way to store, to save away the things that are going to be needed for resuming the computation of a factorial after I've done a subfactorial. What's that? One thing I need is n. So I'm going to build here a thing called a stack. The stack is a bunch of stuff that I'm going to write in sequentially. Okay, I don't know how long it is. The longer it is, the better my illusion of infinity. And I'm going to have a way of getting stuff out of n and into the stack, and vice versa. So I'm going to need a connection like this, which is two-way. Whereby I can save a value of n and then restore it some other time through that connection. This is the stack. I also need a way of remembering where I was in the computation of factorial in the outer program. Now, in the case of this machine, it isn't very much a problem. Factorial always returns, has to go back to the place where we multiply by n, except for the last time when it has to return to whoever needs the factorial or go to done or stop. Okay? However, in general, I'm going to have to remember where I have been, because I might have computed factorial from somewhere else. I have to go back to that place and continue there. So I'm going to have some way of taking the place where the marble is in the finite state controller, the state of the controller, and storing that in the stack as well. I'm going to have ways of restoring that back to the state of the marble. So I have to have something that moves the marble to the right place. Well, we're going to have a place which is the marble now. It was called the continue register. Called continue. Which is the place to put the marble next time I go to continue. That's what that's for. And so there's got to be some path from that into the controller. I also have to have some way of saving that on the stack. And I have to have some way of setting that up to have various constants, a certain fixed number of constants. And that's very easy to arrange. So let's have some constants here. We'll call this one after fact. Okay, and that's a constant which will be fed into the continue register. And also another one called fact done. Okay, so this is the machine I want to build. That's its data paths at least. And it mixes a little with the controller here because of the fact that I have to remember where I was and restore myself to that place. But let's write the program now which represents the controller. I'm not going to write the defined machine thing and the register list because that's not very interesting. I'm just going to write down the sequence of instructions that constitute the controller. Okay? So we have assign, to set up, continue, to done, we have a loop which says branch if equal 1, fetch n. If n is 1, then go to the base step of the induction, the simple case. Otherwise, I have to remember the things that are necessary to perform a subfactorial. I'm going to go over here and I have to perform a subfactorial. So I have to remember what's needed to do that. Remember what's needed after I will be done with that. See, I'm about to do something terrible. I'm about to change the value of n. But this guy has to know the old value of n. But in order to make the subfactorial work, I have to change the value of n. So I have to say, remember the old value. And I also have to remember where I've been. So I save up continue. And what this is an instruction that says, put something in the stack. Save the contents of the continuation register, which in this case is done. Because later I'm going to change that too, because I need to go back to after fact as well. We'll see that. We save n, because I'm going to need that for later. Assign to n the decrement of fetch n. Assign continue. We'll look at this now to after, we'll call it. That's a good name for this. A little bit easier and shorter and fits in here. And now look what I'm doing here. I'm saying if the answer is 1, okay, I'm done. I'm going to have to just get the answer. Otherwise, I'm going to save the continuation, save n, make n 1 less than n. Remember, I'm going to come back to someplace else and go back and start doing another factorial. Okay? However, I've got a different machine in me now. N is 1 and continue is something else. Okay? N is n minus 1. Now, after I'm done with that, I can go there. I will restore the old value of n, which is the opposite of this save over here. I will restore the continuation. I will then go to here. I will assign to the val register the product of n and fetch val. Val fetch product assign. And then I will be done. I will have my answer to the subfactorial in val. At that point, I'm going to return by going to the place where the continuation is pointing. That says go to fetch continue. Okay. And then I have finally a base step, which is the immediate answer. Assign to val, fetch n, and go to fetch continue. And then I'm done. Now let's see how this executes on a very simple case. Because then we'll see the use of this stack to do the job we need. This is statically what it's doing, but we have to look dynamically at this. So let's see. First thing we do is continue gets done. The way that happens is I push this. Let's call that done the way I have it. I push that button, done goes into there. Okay, now, I also have to set this thing up to have an initial value. Let's consider factorial of 3, a simple case. And we're going to start out with our stack growing over here. Stacks have their own little internal state saying where they are, where the next place I'm going to write is. So now we say, is n 1? The answer is no. So now I'm going to save continue. Bang. That done goes in here. And this moves to here. The next place I'm going to write. Save n, 3. Okay? Assign to n the decrement of n. That means I push this button, this becomes 2. Okay? Assign to continue aft. So I push that button, aft goes in here. Okay? Now, go to loop. Bang, so I'm up to here. Is n1? No. So I have to save continue. What's continue? Continue is aft. Push this button. So this moves to here. I have to save n. N is over here. That's a 2. Push that button. So a 2 gets written there. And then this thing moves down here. Okay, save n. Assign n to the decrement of n. This becomes a 1. Assign continue to aft. A, F, T. It's written there again. Go to loop. Is n equal to 1? Oh, yes. The answer is 1. Okay, go to base step. Assign to val, fetch of n. Bang. 1 gets put in there. Okay? Go to fetch continue. So we look in continue. Basically, I'm pushing a button over here that goes to the controller. Okay, the continue becomes aft, and all of a sudden, the program's running here. I now have to restore the outer version of factorial. So we go here, we say, what do we? Restore n. So restore n means take the contents that's here, push this button, and it goes into here. 2, and the pointer moves up. Okay? Restore continue. Pretty easy. Go push this button, and then aft gets written in here again. That means this thing moves up. I've gotten rid of something else on my stack. Right, then I go to here, which says assign to val the product of n and val. So I push this button over here, bang, 2 times 1 gives me a 2. Get written there. Okay, go to fetch continue. Continue is aft, I go to aft. Okay? Aft says restore n. Doing a restore n means I take the value over here, which is 3, push this up to here, and move it into here. N. Now I was pushing that button. The next thing I do is restore continue. Continue is now going to become done. So this moves up here. When I push this button, done may or may not be there anymore. I'm not interested, but it certainly is here. Next thing I do is assign to val the product of the fetch of n and the fetch of val. That's pushing this button, over here, bang, 2 times 3 is 6. So I get a 6 over here. Okay? And go to fetch continue, whoops, I go to done, and I'm done. And my answer is 6, as you can see in the val register. Okay? And in fact, the stack is in the state it originally was in. Now, there's a bit of discipline in using these things like stacks that we have to be careful of. Okay? And we'll see that in the next segment. But first, I want to ask if there are any questions for this. Are there any questions? Yes, Rod?
What happens when you roll off the end of the stack with...
well, what do you mean roll off of?
With a larger starting point of n requires more memory, correct?
Oh, yes. Well, I need to have a long enough stack. You say, what if I violate my illusion?
Yes.
Well, then the magic doesn't work, right? The truth of the matter is that every machine is finite, and for a procedure like this, there's a limit to the amount the number of subfactorials I could have. Remember when we were doing the y operator a while ago, we pointed out that there was a sequence of exponentiation procedures, each of which was a little better than the previous one. Well, we're now seeing how we implement that mathematical idea. The limiting process is only so good as far as you take the limit. If you think about it, what am I using here? I'm using about 2 chunks of pieces of memory for every iteration of this, or every recursion of this process. If I would try to compute factorial of 10,000, that's not a lot of memory. On the other hand, it's an awful big number. Okay, so the question is that a valuable thing in this case? But it really isn't. It really turns out not to be a terrible limit because memory is el cheapo, and people are pretty expensive. Okay? Thank you. Let's take a break.